Hi everyone, today we're going to talk about one-sided limits. Sometimes we don't need to look at the left-hand side and the right-hand side in order to determine a limit. Sometimes all we care about for a specific situation is just the right-hand side or just the left-hand side. So for that we have a different notation. The notation that looks like this. So it's limit of f of x as x approaches c with a negative, right? Superscript negative. So c minus represents the value of the function as x approaches c from the left-hand side, right? So if you think about it, if this is our axis, the left-hand side, this is where all the negative numbers are, and the right-hand side is where all the positive numbers are. So I say the limit of f of x as x approaches c from the minus side, that's from the left-hand side. And then if I say the limit of f of x as x approaches c from the positive side, what I mean is as x approaches c from the right-hand side. So for example, if I was looking at, okay, if this is 1, 2, 3, 4, x equals 4, if I said the limit of f of x as x approaches 4 from the minus side, I'm looking at approaching 4 from the left-hand side. And then if I were to say the limit of f of x as x approaches 4 from the positive side, then I would go at it from the right-hand side. So that's what it means. Okay. Now, here's the definition of a limit. A function has a limit as x approaches c, if and only if, this is the important part now, the right-hand side and the left-hand side limits at c exist and they are equal. So going back to our limit here as x approaches 4. So suppose I looked at the left-hand limit and I got a value of 0.7. And then I looked at the right-hand limit and I got a value of 0.7. Then I would say, because the left-hand side and the right-hand side are the same, then I would say the limit of f of x as x approaches c is L. Okay, so for that to happen, the limit from the positive side and the limit from the negative side have to have the same value. Okay. Let's do this example here. We have got a lovely piecewise function here. What we're going to do is we're going to find the required one-sided limits here. All right, so first off, we want to look at the limit of f of x as x approaches 0 from the negative side. This is x equals 0. From the left-hand side means immediately to the left of 0. So again, you can do this using the imaginary line in the beginning, and then we can get to ignoring that imaginary line or throwing away that crutch. So if I do have an imaginary line here at x equals 0, I want 0 from the negative side. So immediately to the left of 0, that imaginary line, what is the y value of the function? It's 5. Now I want as x approaches 0 from the right-hand side. So if that's my imaginary line, immediately to the right of that imaginary line, the graph has a y value of 5. So that's the left hand and the right hand limits. Now, here I'm being asked the limit as x approaches 0. For this, I look above. The left hand limit is 5. The right-hand limit is 5. Because those two equal the same number of 5, then I say this is also 5. Okay. Now let's go on to the next one. The limit of f of x as x approaches negative 3 from the minus side. So now I want x approaches negative 3. This is negative 3 right here. Let's draw that imaginary line. Okay, I want the function as x approaches negative 3 from the left-hand side. So look at this imaginary line. Where is the graph immediately to the left of that imaginary line? If this is the imaginary line, immediately to the left of it here, there is nothing. But here, immediately to the left of it, there is a graph right there, and that has a value of 0. Now, when I say immediately to the left, I mean immediately to the left. When you zoom in here, you're looking at that point right there, okay? In calculus, we really look at this concept of infinity. We really believe that there is infinite space between the number 1 and the number 2. So when I say next to it, I mean like at 1.0000001. Okay. Now, what about the limit as negative 3 approaches, as x approaches negative 3 from the positive side? Well, that means to the right of the vertical line, immediately to the right of the vertical line. Well, this is the vertical line. Immediately to the right of it, the graph here is at y equals 5. Here, there is nothing to the right of it, so I don't count that one. This point here is just a point. It only exists at that minuscule location, so that doesn't count either. So this is it. Immediately to the right, it's 5. And now I'm asked, what is the limit as x approaches negative 3? Well, let's look. Left-hand limit equals 0. Right-hand limit equals 5. Last time I checked, 0 did not equal to 5. So I say here, not undefined, not no solution, DNE for does not exist. We never write out does not exist. It's always DNE, not UND for undefined. It's DNE. Okay? Now, let's do a little bit more here. Let's go above and beyond here. Let's actually take a look at f of 0. Okay, what's f of 0? Well, let's see. When x equals 0, let me erase this junk here. When x is 0, what is y? Oh, it's 5. So look at that. The left-hand limit, the right-hand limit, the actual limit, and the actual value are all equal to 5. Okay. Here, what about f of negative 3? What's f of negative 3? F of negative 3, so at x equals negative 3, what is the value of the function? Well, we have an open circle here, that can't be hit. We have an open circle there, that can't be it. This is it. It's right there. That's the value. So f of negative 3 is positive 2. In other words, when x equals negative 3, y equals positive 2. So look at that. The value definitely exists, even though the limit is DNE. It does not exist. Okay, moving on. Let's evaluate some of these one or two-sided limits. Okay, so this first one, we're going to have to draw a piecewise function. But you know what? We could totally do that. We know how to do that. My partition is that x is 1, and to the left of x is 1, we have a quadratic equation. So remember how we drew these. We always have to first evaluate this at x equals 1. So when I put 1 into x, I get that y is equal to 1 plus 2, 3. So when x equals 1, y equals 3, but that's an open circle because this is less than, not less than or equal to. And then this is a cubic function. And what do cubic functions look like? They look like this. Now this has been raised. It has a vertical shift of 2. So that point is right here. So basically that looks like this. Okay? All right. To the opposite side, I have 2x plus 1. Again, I take 1 and I put it in there, and y is equal to 3. Okay. Again, 1 is open, 1 is closed. If they overlap, you just close the circle. And I have a linear equation with a slope of 2, so I go up 2 over 1. There. Now, I need the limit. As x approaches 1 from the left-hand side, there is my imaginary line. From the left-hand side, immediately to the left of this point, what's the y value? It looks like 3. Okay, as x approaches 1 from the positive side, immediately to the right of this, what's the value? It looks like positive 3. What's the limit as x approaches 1? Well, left-hand side, right-hand side equal each other, so it's 3. Let's move on. What about this one? So this one's already been graphed for you. Whoop-de-doo. Okay, so we're looking at the limit as x approaches -2. Where is -2? This is -1. This is -2. Let's draw that line. Okay, and the next one. All right, so let's draw that line. So -2 from the minus side, the limit as x approaches -2 from the left-hand side. Immediately to the left of this line, the y value is positive 3. Immediately to the right of this line, well, that's that point. What is the value? -1, 2, 3, 4. So what is the limit as x approaches -2? dne. Because 3 and -4 are not the same. Okay, look at this here. I want the limit of this function as x approaches 3. Okay, so now suppose on a test or a quiz you were just given this and you were not given any of that. What would you do? You would still do all of this. We cannot find the limit without first checking the left, checking the right, seeing that they're equal. Let me rephrase that. The only way to find the limit is checking the left, checking the right, and seeing that they're equal. All right, so this is the limit at x equals 3, and you look at that and you're like, oh my God, at x equals 3, there is something weird happening there. And sure enough, if you look at the function, there is a vertical asymptote at x equals 3, isn't there? Yes, there is. So you still, however, do the same exact procedure. Look, I drew my imaginary line at x equals 3. So now let's do the limit from the left-hand side. Let's do the left-hand limit. Immediately to the left of this, immediately to the left, where is this function? It's all the way down here at -infinity. All right, well, immediately to the right of this, where is the function? It's all the way up there at +infinity, right? When you pick this point, that's not immediately to the right, because look at how far away you've gotten. That's at x equals 4. We're talking about a minuscule amount to the right or left. All right. Left-hand limit, -infinity. Right-hand limit, +infinity. Those are very different values. So the limit does not exist. Okay, let's do one more. All right, look at this function. We want the limit as x approaches 0. Okay, this is 0. Okay, now, immediately to the left of this point, where is the graph? It's right there at -infinity. Immediately to the right, where is it? Right there at -infinity. So now you say to yourself, oh my God, -infinity, they match. So the limit as f of x as x approaches 0 must be negative infinity. And you know what? You're right. The limit is negative infinity. However, what if I told you, hey, here's a spaceship. Come on in here, get in my spaceship, take me to negative infinity. Would you be able to tell me where that is? You wouldn't, because that is an undefined value. So, when your answer does turn out to be infinity, I want you to please also include DNE. Okay, yes, the limit is negative infinity. But is that a finite number? Is that a number that I can put my finger on? It's not. So I have to say comma DNE, or in parentheses DNE. All right? Now, I know you're asking me, well, what if I don't put DNE? Is it points off? It can be. So just make sure that you go ahead and put it, okay? Now, when you get DNE like this, you don't have to add infinity to it. It only works one way, not both ways. Okay, let's move on to the last one. Look at this one. As x approaches 0, from the negative side and from the positive side. Okay, so this is sine of 1 over x. It's kind of a VIP of functions. It's a very famous function. So x equals 0. The limit as x approaches 0. Okay, so look at the values here. It goes from negative 0.75 to 0.75. So this is negative 1 and positive 1. This is like definitely zoomed in here, right? So what's happening? The graph comes over here, and then what does it start to do? It starts to oscillate like mad. So if you zoomed in over there, you would see that it was oscillating like crazy. Now, what does it mean that it's oscillating? It's going up and down and up and down and up and down. So at any given time, the y value could be here or here or here or here or here or here. Now, who can tell me where that vertical y value is as you approach x equals 0? Do you know? Immediately to the left of it where it is? No. Do you know where it is immediately to the right of 0? No. So, this is DNE all around. Right? And the reason why it's DNE is because there is no way of knowing where that y value is, because the function is oscillating so quickly. Okay, so let's wrap up. There were a couple of cases now where we got DNE does not exist. So let's just recap where you can get DNE. The limit as x approaches c does not exist if, first and foremost, if f of x approaches different values from the left and right. Okay, so where in these examples did that happen, where we got different values and so we got DNE? Oh, right there. Okay, in example B. Another situation where you might get DNE is if f of x increases or decreases without bound, approaches positive or negative infinity from the left, the right, or both. So where did that happen? Where did that happen when we got DNE because it approached negative or positive infinity? Well, here and also here, right? In one situation, it approached different infinities. In the second, it approached the same infinity, but still, we got DNE. And a third situation to get DNE is if f of x oscillates rapidly between two fixed values, like in E, right? So that has to be a rapid oscillation. So if it's just y equals sine x, that's not fast enough. We could definitely pinpoint where y is, right? That's why we were able to do chapters 4 and 5. It has to be quick oscillations. All right. Thank you for listening. There's that second part. Have a good day.